Part C. A block of material is removed, or the block of material is removed, so we're going back to normal air in there. And a very thin slice of the transparent material from the block is used to cover the top slit. So same thing, refractive index, let's get rid of our grating. So we've got a little bit of material here. That's covering our block. When this is done, the central maximum is observed to move up. So it's no longer what it was. Sort of a central maximum there. It now shifts upwards. Explain. Okay. What I would think then is what we need to look at is a condition for the maximum. Okay, so again, let's suppose waves come off like that. So we're looking at an angle theta. Now, what we need to have is that it says it's a thin. Let's make it a really, really thin bit. Just to make our diagram a bit simpler, so here we go, so we can do it like that. So this wave is travelling that little bit further than that wave. So this wave goes that distance, this wave goes a little bit of a distance. Now what we want is when this one comes out of the material and that one there, is that they are in phase. That's the key thing. Two waves are in phase. So if we say that the phase is 0 here, what is the phase of this one when it's back here? What is the phase of the second one? So condition for maximum, two waves are in phase. So your first one, call that 1 and 2, has an extra D equals that length, we'll call it L, that's D, so has an extra L equals D sine theta length. How many wavelengths is that? Over lambda naught, our original wavelengths. This one is going to go and have a small phase difference. It's not going to start from 0 anymore because it's going to be delayed ever so slightly. So top one also has a delay. And it's going to depend on the thickness, but we could call it X wavelengths. So what we want is the difference between these two to be a whole number of wavelengths. So D sine theta over lambda naught minus that little phase difference is a whole number wavelengths. from which we can so a whole number of, hang on. Yeah, so this is in number of wavelengths. This is that distance in number of wavelengths. So if we say the delay is x number of wavelengths, then d sine theta over lambda naught, take x equals n. Now if x was 0, of course we end up with the same criteria as we had before. Let's go on over here. If x was 0, no material, then we've got d sine theta over lambda naught equals n, which implies sine theta equals lambda naught n over d. Theta equals naught. If n equals 0, make it m again. That's what we had before, the normal case. X not equal to 0. Now we've got a delay. So what's our equation now? Move that over there. So d sine theta over lambda naught equals m plus x implies sine theta equals m plus x lambda 0 over d. So now m equals 0 implies sine theta does not equal 0. It has shifted. In fact, upwards, we've got a little bit of a shift up there. And there's the explanation.